Okay, ladies and gentlemen, in today's lecture on EEC 393 Digital Signal Processing, we shall be discussing about the discrete time Fourier transform, which in short otherwise is known as Dtft. Now then, the discrete time Fourier transform Dtft is essentially used for the non-periodic or aperiodic discrete time signals. Unlike the continuous time Fourier transform, the only difference is the continuous time Fourier transform, which is used for continuous time signal, the discrete time Fourier transform is used for the discrete time signal. But in both the cases, we shall be working with the aperiodic signal. Now, unlike the Fourier series, okay, let me summarize the previous point down, used for discrete time aperiodic signals. Okay, in the next point, I'd like to emphasize that unlike the Fourier series, where we represent the signal in the frequency domain with the fundamental frequencies, that means in Fourier series, we represent signal in frequency domain by the virtue of fundamental frequencies. Which means that in the frequency domain, the values of the frequency are the multiple of the fundamental frequencies, which we have termed in the previous lectures to be harmonics. But this is not the case for the Fourier transform, where we will be requiring a whole continuum of frequency, not any particular fundamental frequency or any multiple. We shall be dealing with a range of frequency to be exact. So, in Fourier transform, we use a continuum of frequency to represent the signal in the frequency domain. These points will become much more clear once we go into the derivation. So without a further ado, let's go to the derivation. Derivation of Dtft. Now then, the derivation in this case is quite similar to that of the CTFT, with certain differences here and there. As we will go along the derivation, we will look upon the differences. Now, suppose x of n is an aperiodic discrete time signal. In the previous derivation of CTFT, we have considered it to be x of t, where t being an continuous variable. N in this case are discrete variables, rather taken as samples of the signal after a certain period of time. Now, let us observe what x of n looks like. if this is the sample n, x of n, time axis, then say I am assuming x of n to be something like this. This is the value at 0, at 1 and 2. This is the value at -1 and consequently -2. Then there is 3 gaps in the remaining samples. Let this point be n by 2 and this be -n by 2. So this is our given signal x of n, and since it is not occurring after a certain period, that is, the signal is simply defined within the range of -n by 2 to n by 2, so it is quite simply an aperiodic signal. And since the signal doesn't occur for every time instant in the time axis, rather it is found to be for certain values of time as samples, this also dictates that the signal is discrete in nature. Now what shall we do is, like before, we shall try and convert this signal to be a periodic signal and start working with the Fourier series upon that periodic signal. So if this signal is converted to a periodic signal, the signal will look, this is the time axis, signal will look something like this. This is the first sample, this is the second sample, third sample, three gaps. Again we get sample, there are three gaps over here as well. So this is the same signal which we have repeated after every n period. So this will be a positive n and this will be negative n. This is 0, this is n over 2, this is negative of n over 2. Let us say this signal is xp of n. So we can write xp of n is periodic in nature with a fundamental period of n. Now, as before, mathematically speaking, if we derive a relation between the xp of n and x of n, then we can write limit capital N, which goes to infinity, xp of n is equal to x of n. This is n, November. So this relation essentially means that if n tends to infinity, that is n approaches infinity, the gap between these two signals becomes larger and larger, and all we are left with is this part over here, which is essentially similar or identical to the previous signal, that is x of n. Okay, now since we have established a periodic form of x of n, So we can write the Fourier series expansion, the Fourier series expansion of xp of n can be written as xp of n, where k goes from 0 to n minus 1 for the running sum of ck e to the power jn k capital omega naught, where omega naught is the angular fundamental frequency, which can be written as twice pi over n. And ck is of course our Fourier series coefficient, and the Fourier series coefficient can be written as ck equal to 1 over n, the time period, n which goes from 0 to n minus 1, xp of n e to the power minus jn k omega naught. Now then, if you observe carefully, n equal to 0 to n minus 1, so n which goes from 0 to n minus 1 essentially dictates the number of samples which we are working with. So 0 being the first sample and n minus 1 being the last sample, there are n samples. So we can change the limit, as I have told before, that this limit can be changed, but the number of samples should be equal. So for our ease of calculation, we should change the limit to n equals minus n by 2 to positive n by 2, which is essentially the same number of samples that it was before, but we have done it for the ease of our calculation in the future. xp of n, the rest remains as it is, e to the power minus jn k omega naught. So then, now from the limit negative n minus 2 for the limit negative n minus 2 to n minus 2. That means we are talking about this part of the signal. This part of the signal, negative n minus 2 to n minus 2, xp of n behaves exactly similar to that of x of n, because x of n also ranges from minus n by 2 to n by 2. So if we were to replace xp of n by x of n, the mathematical expression still holds good. So we can change the equation of c of k to be 1 over n summation, where n goes from negative n by 2 to positive n by 2, x of n e to the power minus jn k omega naught. I hope that is clear. Now in x of n, since we have replaced x of p by x of n, so if you look carefully, outside of negative n minus 2 in this direction, the value of x of n is 0, and same goes for this direction outside of positive n by 2. So if we were to change the limit from negative infinity to infinity, the equation still holds to be true. So we are going to do that is 1 over n. We can change the limit. N goes from negative infinity to infinity, which essentially means the summation from negative infinity to infinity, but all we are working with is this point and this point, from this point to this point. Others, the value are 0. So this becomes x of n e to the power minus jn k omega naught. Let us mark this as equation 1. Okay, moving on. Let us define a continuous function of frequency. Let us define a continuous function of frequency to be capital X of capital omega, such that capital X of capital omega is equal to summation, where n goes from negative infinity to infinity, x of n e to the power minus j omega n. Let us mark this as equation 2. And our equation 1 was this one. So comparing equation 2 and 1, the only difference is this term 1 over n, and x and omega, the exponent is a function of omega k over here. But here the function is only omega. So we can simply write, comparing 1 and 2, c of k is equal to 1 over n capital X. This was a function of omega, but since it has got a continuous multiple of k, this can be written as k omega naught, this being omega naught, sorry. So where omega is equal to k omega naught. Now replacing this value in our earlier Fourier series expansion of xp of n, we can write xp of n such that 1 over n, where k goes from 0 to n minus 1, and a running sum over capital X k omega naught e to the power j n k omega naught. I hope that is clear. Now some algebraic manipulation. K goes from 0 to n minus 1, x k of omega naught e to the power j n k omega naught times omega naught by twice pi. So what I have done is taken this value inside of the summation operator and plugged in the value of 1 over n, which we got from is omega naught, we know, is twice pi over n. So n is equal to twice pi over omega naught, and consequently 1 over n is the inverse of this term. So we have replaced 1 over n with the value. Now this part is quite a bit tricky. If you observe carefully, now we are changing the limit n to infinity. That means as n approaches infinity, which is essentially true that omega naught will be approaching 0, because the relation is obviously inversely proportional. So as one approaches infinity, the other is bound to approach 0. So x of n, we can write limit n tends to infinity. See, since we have taken the limit as n approaches infinity, x of p will become x of n in the left hand side. As I have shown earlier over here, as n approaches infinity, x of p will turn to x of n. And in the right hand side, what we'll be getting is limit xp of n, which is equal to limit omega naught, which tends to 0, xp of n. Just changing the variable of the limit. Now moving forward, this can be expanded as omega naught, which goes to 0, putting in the value of xp of n, summation where k goes from 0 to n minus 1, xk omega naught times omega naught divided by twice pi. What I have done here is just multiply this term with this term. E to the power jk omega naught n. Now then, since omega naught is approaching 0, we can replace omega naught by the infinitesimally small difference operator, that is delta omega. So we can replace omega naught by delta omega, and the equation yields to be x of n, where limit delta omega, which goes to 0, summation k, which goes from 0 to n minus 1, x of k delta omega over twice pi times e to the power j and k delta omega. Now this can be written further as limit delta omega tends to 0, taking this 1 over twice pi out of the summation operator, 1 over twice pi summation where k goes from 0 to n minus 1, a running sum over x of k delta omega e to the power j n k delta omega times delta omega. Now, as I have shown earlier, this is something like the Riemann sum. And what was the Riemann sum? If we were to take the integral of this curve, say from the point A to the point B, this is our time, and this is, say, the function x of n. Say, for instance, what we do is divide this function into some components of rectangles, these being the rectangular values. So this is the first slice, this is the second slice, third slice, fourth slice, and consequently the nth slice. And each of this difference in our case is delta omega. So in order to find the area under this curve, if this is the height and this is the width, all we need to do is find the area of these individual rectangles and take a summation over it. So we can write this as x1 of n plus x2 of n plus x3 of n, where x1 of n is the height of the first rectangle, x2 of n is consequently the height of the second rectangle, and this goes and goes. This can be mathematically simplified as I, which goes from 1 to n, xi of n times delta n. So this being the area under the rectangle. Now if you observe carefully, if we take the slices of each of the rectangle to be infinitesimally smaller, that means if we increase the value of n, the more we increase the value of n, the more accurate we shall be getting the area. So here n is time, so if n increases, consequently delta omega, the frequency will decrease. So if frequency decreases, the value will be more closer such that we can define the area more precisely. And from the integral calculus, we have learned that the area under a curve is nothing but the integration. So this can be written as integration of x of n delta omega over a period of n. So this is the Riemann sum. So this expression is likewise, this is the value of our function along the height of the function, and this is the spacing between them. So as delta omega approaches 0, this can be changed to be an integral. So x of n we can write simply as 1 over twice pi and integration x of omega e to the power jn omega d omega, where the value k del omega is changed to the continuous operator, that is omega. And this is because we were working with summation in the previous terminologies, and since integral is a continuous operation over a certain period of time, we will be needing a continuous operator. So this can be changed to omega. Now what about the limit? If we talk about the limit, what we will get is that k goes from 0 to n minus 1. That is for a total of n number of samples, which are spread at delta omega distance apart. So essentially n delta omega, n times delta omega can be written as twice pi. N delta omega can be written as twice pi. The explanation for that will come a bit later, where we will try and prove the limit using this, but you have to take my word for it until we get to the derivation of that. So we can simply write the limit to be twice pi. And hence we are done. X of n, which can be written as 1 over twice pi. There is the limit twice pi from 0 to twice pi, or we can take from negative pi to pi. X of omega e to the power jn omega d omega. So this is our equation for the inverse Fourier transform, or in short inverse transform, and this is the expression for the direct transform. So this is the expression for the direct transform, and this is the expression for the inverse transform. Now, to summarize the synthesis equation, x of n is equals to 1 over twice pi minus pi to pi x of omega e to the power j n omega d omega, which is the inverse transform, and the analysis equation, which gives us x of omega to be equal to summation where n goes from minus infinity to infinity and taking a running sum of x of n e to the power minus j n omega, which essentially is our direct transform. Now, if you look carefully, upon closer inspection, x of omega is a function of omega, but omega in both this equation will always occur as a power of e. So we can write x of omega to be a function of x of e to the power j omega. This also will hold true, and this one is also correct, but we shall be working with this expression for our further analysis. So we can write the direct transform equation to be equal to the direct transform x of e to the power j omega, and the summation where n goes from negative infinity to infinity, x of n e to the power minus j n omega, and the inverse transform we can write x of n to be equal to 1 over twice pi, an integral over minus pi to pi, capital X e to the power j omega e to the power j n omega d omega. So these are the two equations that we derived for the discrete time Fourier transform.